History of Speed of Light. I like this quotation by Douglas Adams that says, "Nothing travels faster than the speed of light, with the possible exception of bad news, which obeys its own special laws." So let's talk about a little bit of history. Speed of light is a very important fundamental constant known with great precision today due to the contributions of many, many scientists. Until the late 1600s, light was thought to propagate instantaneously through ether, which was a hypothetical massless medium distributed throughout the universe. Galileo was the first to question the infinite velocity of light. With this began what was to become a long list of many more experiments, each improving the accuracy of C. So is speed of light infinite? Galileo Simplicio states that Aristotelian and Descartes' presupposition, everyday experience shows that propagation of light is instantaneous. For when we see a piece of artillery fired at a great distance, the flash reaches our eyes without lapse of time, but the sound reaches our ear only after a noticeable interval. So Galileo, published in 1638, proposed that the question might be settled in true scientific fashion by an experiment over a number of miles using lanterns, telescopes, and shutters. So in 1667, they did an experiment. And that experiment made the first attempt to actually measure the speed of light. Two people, A and B, with covered lanterns, went up to the top of the hills about 1 meter apart. So one person was at point A and the other person was at point B. First, A uncovers its lantern. As soon as B sees light A, he uncovers his own lantern. By measuring the time from when A uncovered his lantern until B sees the light, divide this time with twice the distance between the top hills. Therefore, the speed of light would theoretically be equal to 2 times d, which is the distance between them, divided by the time it takes. So include that the human reaction times are approximately 0.2 seconds and therefore too slow for determine C with any accuracy. This experiment, however, was really, really good at proving the fact that the light did not travel instantaneously. It actually traveled at some speed. Well, that was a big breakthrough. So what happened next? So during the same time, thousands of men were lost at sea, and because there was no accurate way of determining longitude at sea. Galileo proposed using an eclipse of one of the Jupiter's moon to determine the difference in longitude between these two places. Olaf Romer took up the task of using Jupiter's moon to determine longitude. 1676. The first hard evidence for the finite speed of light. So Romer noticed a variation in ellipse times of Io, which is the innermost moon of Jupiter. When the Earth moved away from Jupiter, the moon appeared to stay behind the planet 22 minutes longer than when the Earth was moving towards Jupiter. So using that phenomenon, he used the equation d1 minus d2 divided by t1 minus t2, where t2 was the time of ellipse when the Earth is moving towards Jupiter, and t2 is the time of ellipse when Earth is moving away from Jupiter. d2 is the distance Earth moves during t2, and d1 is the distance Earth travels during t1. So from this observation, Romer determined that c is equals to 2.1 times 10 to the 8 meters per second. Now, it is a third too slow because he was using inaccurate information on the radius of the Earth's object. But it was a really, really good way of determining the fact that the speed of light was not infinite as it was previously thought. 1728, Bradley and the stellar aberration. Stellar aberration is approximately the ratio of the speed of the Earth as it orbits the Sun to the speed of light. Stellar aberrations cause apparent positions of stars to change due to the motion of the Sun around the star. Bradley used these stellar aberrations to calculate the speed of light by knowing the speed of the Earth around the Sun and the stellar aberration angle. His independent confirmation, almost 50 years of struggling with this, finally absolutely ended the opposition to a finite value of the speed of light. He calculated the speed of light in a vacuum to be equal to 301,000 kilometers per second. Then after almost 120 years later, Fizeau did an experiment, and this experiment included a narrow slit to produce a narrow beam of light. Light travels through the spaces of a cogwheel and reflects off a mirror. He adjusted the rotational speed of the cogwheel until the light passes through the next spot of the wheel. He calculated the speed using the formula C equals 2dV over d, where d is the distance between the wheel and the mirror, and v is the velocity of the wheel, and d is the distance between spaces in the wheel. Without getting into too much bogged down with details, he calculated that the speed of light will be 3.15 times 10 to the 8 meters per second, which is very, very similar to the normal speed of light that we know of today. So from 1676 to about 1983, there were many experiments done with many different methods that were employed. And we have a result anywhere from 214,000 to about 299,792 thousand kilometers per second, which is now the accepted value of the speed of light. So here's the data that shows the speed of light that were calculated from about 1945 to about 1985. The measurements were done, and it was found that those values that were measurements when they were made in a vacuum kind of fell about these points, and those ones that were not done in a vacuum and actually in medium, the values were calculated to be about here, which sort of makes sense, right? So modern measurements from 1947 to 88, it includes, if I zoom into that part of the graph, it kind of gives me this graph right here, which varies, but still they're within standard deviations of each other. History in a nutshell: since 1930, the general acceptance of the theory of relativity, C has been accepted as a constant and invariant at about 3 times 10 to the 5 kilometers per second, or 3 times 10 to the 8 meters per second, or 186,000 miles a second. Since 1960, there have been hundreds of experiments to precisely measure C. In 1971, it was established that the speed of light was 299,792 kilometers per second, and time was defined by the cesium clock standards. This made the measurement of C more difficult because if C varies, it also affects the cesium standard, making variations undetectable unless time is measured by another method. 1983, C was defined as 299,792,458 meters per second, based upon the laser precision methods. So again, 1983 formed the basis of a new definition of a meter based on the speed of light. So now the meter was defined as the length of the path traveled by light in a vacuum during the light interval of 1/299,792,458 of a second.